As I mentioned earlier in this class, I said that there's three main topics of calculus. You have limits, you have derivatives, and the last one is going to be on integrals. So now that we've finished limits and we've finished derivatives, now we're going to move on to this last major topic of integration. So chapter 4 is all about integration. So here we're going to start with talking about antiderivatives and this idea of indefinite integration. So the idea that we're going to start to work with, to be able to start to motivate this idea, is we want to reverse the derivative process. So we're going to reverse the derivative process. So we can ask this question, what does that mean to reverse it? Well, I'm saying, what function has a derivative given by f of x equals 2x? So I could give you a function, and at this point you know how to take a derivative. But what if I give you a derivative, and I say, what function did that originate from? So here, if we're trying to think about what function has a derivative equal to 2x, well, hopefully you would come up with some type of function, say g of x is equal to x squared, right? Take the derivative of x squared, you get 2x. Cool, that works. So a function, f, is called an antiderivative of this little f if the derivative of this big guy is equal to this function. So basically, this function that I just found, that would be the antiderivative of 2x. So x squared is an antiderivative of 2x. So let's do another example. Let's find an antiderivative of f of x equals cosine x. So again, you think about what function, when I take its derivative, do I get cosine? Well, hopefully what you can come up with would be something like sine x. Right? The derivative of sine x is equal to cosine x. Now, if I forced you to think of another one, what would be another function that has a derivative equal to cosine x? Well, we know sine x is there, but what if I look at sine x plus 1? The derivative of sine x is cosine x. The derivative of 1 is 0. So that works. Come with another example. Let's call this one, say, j of x. Another example could be sine of x minus 73. Right? Take the derivative of sine x, you get cosine x. Derivative of negative 73 is 0. So indeed, all of these are antiderivatives of cosine x. Now, obviously, that's going to get really complicated if we allow there to be all different types of numbers at the end of this, right? Because I could also have plus 60, plus 193. There's a whole bunch of those. So what we have is we have this theorem that says that if this capital F is an antiderivative of f, then g is an antiderivative. So if you have an antiderivative and you have a second antiderivative, that's going to be true if and only if g of x is equal to f of x plus c, where c is a constant. Or in other words, we're saying that the only way to have two different antiderivatives of a function is if they only differ by a constant. So like we saw over here, the only difference between all of these is the constant. Either it's plus 0, plus 1, negative 73. So this is going to allow us to say, okay, no matter what, there's this meaty part of the antiderivative, and then there's this constant that just kind of hangs around. So what we're going to call g, this capital G, the definition is we're going to call this the general antiderivative of f. So if we allow ourselves to just have plus c plus this constant, that is going to be our general antiderivative. So if we take a look at this example, find the general antiderivative of y prime of x equals 2. So I'm trying to come up with the function that has a derivative equal to 2. So using the same notation, I can use, say, y of x. This would be my general antiderivative of y prime, right? You're looking for the function that has a derivative equal to 2. We think about, okay, what do I take the derivative of to get 2? Well, you should get 2x. So this is an antiderivative, but the general antiderivative will say plus c. This will categorize every single type of antiderivative when you write it like this. And we always assume when we see it written like this that c is always going to represent a constant. So this process of finding the general antiderivative, this is called antidifferentiation. So we had differentiation, and obviously if you take the opposite of it, it makes sense to put anti, right? So anti-differentiation. Or what we might also start to refer to this as is what's called indefinite integration. So to start to kind of connect things into chapter 4 of integration, we can call this process indefinite integration. And it's going to be denoted by what's called the integral sign. It looks kind of like a elongated S. So we're going to see this quite a bit, and this is going to tell us I need to be doing anti-differentiation, or in other words, indefinite integration. So we'll look at more examples and be able to come up with a general strategy of how can we start to find general antiderivatives fairly quickly.